Hello, ladies and gentlemen, boys and girls, freaks and geeks of all ages, and welcome to our virtual presentation. My name is Stephen Loftus-Mercer. I'm a principal software architect at National Instruments. For 20 years, I worked on LabVIEW R&D, and I'm now working over with Blue Origin as a G programmer. With me today is a presenter that I've worked with several times in the past, John McBee. He's at one of NI's alliance partners over at Compose Systems, and a co-worker of his, Paul Ross, who will be doing our moderation and monitoring the chat forums for you. And what we're going to talk today about is a little thing that I added to LabVIEW 2020 with my team called LabVIEW interfaces. Now, John and I have presented several times in the past about how to do software engineering in LabVIEW and bringing different techniques from other places. And one of the things that we've talked about a lot is the solid principles. But we've always kind of avoided the D in solid, because D is really hard to do unless you have interfaces. So today, we're going to take a project, a real-world project that John and Paul work on, and show you how we refactored it and taking interfaces into account to be more in line with the D of solid, that dependency inversion. Now, the code we're going to show you is not the original code. We've way simplified it down so that it's easy to absorb during this presentation. But the basic ideas that we're presenting are what actually we're doing in the real software. And with that, John, why don't you show them what we're actually looking at?
All right. You want to advance the slide? There we go. All right, so the project that Paul and I worked on is with a company named LabVIEW, and it's the FLARE network. And the FLARE network is a network of satellite calibration systems. And so our project was automating this system, kind of bringing it to life. It's a very interesting project because one of the applications is they're going to be able to calibrate satellites more quickly and more efficiently, which has huge impacts on things like the efficiency with which people can collect data on climate change. And so this has real world implications, which is really cool. And there's a quick couple-minute video about the project itself, just to give you guys a little eye candy and some idea for context what we're talking about.
Start that video. There. So let me see if I get this right, John. You've got a mirror on the ground, you've got a satellite up in space, And by knowing where the satellite is, you point the mirror directly at the satellite, and then the satellite is able to calibrate its onboard sensors to know what color it should be seeing.
That's close, yeah. So it's a mobile base station on the ground, so they can put them anywhere they want around the world, which is kind of unique in and of itself. And there's the mirror array, but off to the side is an instrument tower. And so what happens is a look request comes in from the cloud API. And so somewhere in the world, a customer logs into a web portal and they say, this is my satellite. It's going to be in this position at this time. It's going to go on this trajectory. I'd like to schedule a look request. That comes down to our ground-based system. We schedule that look request. And when the time comes, we track the satellite with the mirror array. As at the same time, we take instrument measurements with the instrument tower. And so there's a couple different things all happening at the same time.
All right. Well, that tells us a bit about what all the moving parts are that we're looking at. What's the software look like that drives this hardware system?
Yeah, so just a really high level view of the solution space. So the web API, we didn't create. A different team, I think over in Europe, created that, and they just kind of gave us the API that we had to adhere to. And we wrote the business layer. This is all running on a compact Rio. And so on the Rio itself, we're able to connect up to the web API, taking commands. As the commands come in, they get processed and scheduled. So these are dynamic, and depending on what the particular customer wants to do with the system, the sequence that gets built up is going to be different. And so they come in, they get put together, they get scheduled. And down below, we have our resource layer. The resource layer is made up of motion control for the mirror array and subcomponents of it. There is a resource layer for the instrument tower, and the instrument tower itself has multiple components as well. And we broke these up into what we call services. And so from a high level, data comes in from the cloud. Our business layer, which uses one of our packages called the MBA framework, runs a base implementation of MBA to collect the data, to do the scheduling and the processing. That scheduler kicks it over to a different one of our packages called a test executive for sequencing. And we do kind of complicated dynamic sequencing there. As the sequence runs, each individual step is going to collect some data. And what we're going to focus on in this presentation is what we do with that data. Now, this was done over the course of, I think, 5 sprints, and we were pretty time constrained. This is an alpha system that we're talking about here. And so Paul and I wrote all of the code to frame out the system and to control the hardware first. And then our last sprint, we decided it was time to deal with the data itself. And so we kind of intentionally accrued some technical debt on how we handled the data in the system. And our implementation, while it worked for the alpha system, wasn't perfect. And so our plan was to go back and revisit it in beta. And so what we're going to talk about here is a simplified look at how we plan to refactor our implementation for how we use data and how data gets consumed outside of our application using interfaces.
Okay. So just a little note here. When we start talking about their whole system, they're talking about using interfaces in many different places. But the reason we're focusing on this one in particular is that it's going to give us a particular use case of interfaces that many people in the community have asked me for an example of. And so that's why we're going to zoom in on this particular section. So as we said, we have the presentation layer up top. That's in the web. There's a network layer down to the business. And then this is where the data generally gets handled and output. So what are we seeing here, John?
So this is a pretty simplified view, but you can see on the bottom left-hand corner, we have test steps like acquire spectra, read thermocouple, set heater output. In reality, those were, there were many more test steps because we had to deal with the different APIs for the different instruments that we talked to.
John, can you actually see my mouse?
I do not see your mouse.
Okay, I was just trying to figure out if everybody could see where I was pointing.
Yeah, no, I can't. But you can see the build array outside the for loop. Those are test steps coming in, and so that for loop is going to act like a process model, and it's going to iterate through a sequence of steps. The methods with the yellow header there are going to be, think of them as process model methods, where their job is to set up the test step, run it, and then do something with the data. Now, part of our problem that we're trying to solve with interfaces is the other two objects coming into the for loop. One of those is for writing data to file. Later, it could be writing data to database. And the top one is getting information up to a UI, or it could be getting information back through the cloud API to the thin client. So we have two different ways that we need to consume this data that we collect inside of our sequence. And those two ways don't have a common parent, so there's no inheritance between them. And so we end up with a little bit of duplicated code. This is recorded, right? I'm not sure. You mean, are we recording it right now, Norm? I'm getting distracted.
All the presentations are recorded.
Yeah. And so this is kind of the crux of the problem we're going to talk about today, is we end up with kind of a naive approach to data persistence that forced us to deal with it in two different chunks because we didn't have a way to share functionality between the two different methods of data consumption.
Okay. So the read persisted data on every step that we do, we're going to generate an array of an enum that represents a data type, a name of the field that we're recording, and a variant. And then we're going to send that array of information, that produced data, and we're going to update the user interface, and we're going to write it to a file. And that's what we're trying to improve on.
Mm-hmm. Yep.
All right. So let's talk what the problems are with that existing setup. What doesn't work?
So with this one, we were looking at performance that could be improved upon for sure. Definitely more data copies than desirable. And some of these are large waveforms, and so data copies become important. And no compile time type safety. So the data collecting bucket right now, there's no good way, aside from just like semantic coupling, for us to ensure that the data on one end will match the data on the other end. So data in matches data out.
Okay. Yeah, it would be nice if we could just maintain all of that data type safety that LabVIEW provides to us all the way through. So we decided, when we were looking at this problem, how do we go about getting rid of those variants, and what can we do? And we realized that this was actually a pretty good time to be able to start showing off dependency inversion. So I'm going to do a little bit of a background check here. This is a CLA summit for architects, not certified, but architects nonetheless. So LabVIEW interfaces first appeared in LabVIEW 2020 in April. It is now November. So that means you've had 6 months to study all of this. So I expect that most of you are up to date. But because John and I are nice, we're going to do a little bit of a review. All right. So what is an interface? Well, in the general context, you have a software interface. And we actually had a CLA presentation, or an LA presentation earlier today that talked about interfaces generically. And that is a set of functions that you kind of block them together, and one module is going to use that interface to request functionality from another module. With LabVIEW interfaces, we formalize that concept, and we say, okay, we're going to group that set of functions together into a new data type. And objects that express that data type are going to say, I can do the following things, but you don't declare how exactly they're going to be done. That work of explaining how to do them is left to the actual concrete classes. We've talked in the past, over the last 15 years since the introduction of LabVIEW object-oriented programming, about classes, and there are 3 aspects of a data type that when we're trying to decide, is this a class and what kind of class is it? And we've talked about identity, state, and behavior. And those of you who have watched presentations from me over the years, we go through it. Identity is, how do we as programmers think of this class? What is its role in the system? What is its job that we're going to go to? Who else is going to be talking to it? How do we think of this thing? What is its core being here? Then we have state, which is the internal data that this object has and the convolutions of that data over time. How does it move from one state to the next state in response to various of its functions being called? And behavior. Behavior is literally the state, the set of functions that can be invoked. What services does it provide to the rest of the system? What promises does it make that it has to uphold? And when we're talking about inheritance, we say, well, in order for a child class to inherit from a parent class legitimately, because you can do some really nasty hacks, but you get a system that doesn't really work if you don't do this, it has to match the parent's identity, state, and behavior. It can specialize all three of those, or any of those three, but it has to fulfill all the promises of the parent. That's the Liskov substitution principle that we've talked about before. With interfaces, we're going to remove that middle one. Interfaces are only going to define an identity in the system and a behavior, but it doesn't have private data. And interfaces can be largely thought of as a class that simply does not have private data. The private data control doesn't even exist in the data type. You're going to create the type, and you're going to give it a whole bunch of methods, and those methods are largely going to be empty bodies. They may return an error that says, if you're calling the raw code, there's nothing to do here. But there's no actual real work being done, and they can't remember their state from moment to moment. That definition of how to get the job done is left to the classes that inherit those interfaces. Now, the D in solid. I'm not going to go back through all of the solid principles today. They've been talked about in other presentations, and they're actually going to be picked up in some others later today. What we want to focus on for the moment is the D, the dependency inversion. So when we have a direct call, when a caller VI calls a sub VI, the caller VI may be in one class, and the sub VI may be in another class. And that direct call means that these are tightly joined together. With dependency inversion, we say, look, if there's any complexity at all to A and D, or if we think we're going to be refactoring them, or if this is a point of significant change within our application, we do not want to make a direct call. Instead, what we want to prefer is an indirect call, where class A calls to an interface, and class B inherits that interface. Now, it's easy enough to just say, well, we prefer that, but why do we prefer that? Well, what it allows is some amount of separation. If you have a direct call, these things are forced to be a single module. And A always depends exactly on B. It can't be anything other than B. But if with an indirect call, I can actually build these as two separate modules. I don't have to. I can still build the whole system together. But I'm permitted to separate them. And I can certainly test them independently. And that means that the B could be a number of different things. We can change it out statically with a different type of compilation, or dynamically at runtime just by picking a different B. And that's going to have some powerful implications for refactoring and for testing. In fact, we can go a step further and say that the indirect call allows us to compile it as 3 independent modules, where we can actually completely separate who is the caller and who is the callee in very radically different ways, and have very fine-grained control over our distribution capabilities. We can send a newly revised caller out and know that all of our callees are fully backward compatible because they're still talking to the exact same interface. Likewise, we can swap out the callees and know that they're still fulfilling the same interface and thus work for the caller. This principle, as with all the solid principles, is not something you can just do as a hard and fast rule. That's why they're principles and not rules. You look at your code and you say, what are the places in my code that are most likely to have to change? What are the places where I've got this tight friction, or where I've got really complex logic and I'm going to need to be able to reach in there and test it better? And when you get some amount of time having thought about these things, you start to become aware of, this is a particularly tight place where I need just that little extra bit of space. And then those are the places where you reach in and say, look, I'm going to move B down a little bit in the hierarchy, put an interface above it, and tie A to that.
So one note, Stephen, on this, it directly ties into our need to refactor how data moves through our application, because we were time constrained. We just decided to write to file for our alpha implementation. But we know right now that coming into beta, we have to move over to a database. Now, because of the time constraint, Paul, correct me if I'm wrong, I don't think we built in the proper interfaces to make that easy, but I think we did that on purpose. And our plan is to come back and to readdress this and do this correctly with the proper dependency inversion.
Right. Because if you've got an interface that allows you to write to thing, you know your caller is making all the right calls to do write this value, write this value, write this value, and that can all be tested and set up. And if it's writing to a file, you can test the file. And then on the day you decide to write to a database, all you're doing is replacing the file with the database call. Now, we can do all of that work with an abstract class, and we've done that in past versions of LabVIEW. But with LabVIEW 2020 and interfaces, we get a better ability to do that because we can swap on multiple axes. Abstract class only allows a single chain of inheritance. Interfaces allow multiple chains of inheritance, so we can shift things around a lot easier.
Yeah, and that, just to chime in real quick, that's an important point, because coming into interfaces green, it was hard for me to see right off the bat why I would want to use one over an abstract class, which is how we've solved problems leading up to now.
And one of the things that we realized was when we're trying to get rid of those variants, we should not send directly from this to that just without going through the variants. There's actually some problems that we ran into even trying to look at that model. But when we start an interface into it, and we use that send indirectly, as we're going to see when we get back to the code, we were able to shim that layer much nicer, and we were able to maintain the type safety. So this answers our original question. Can we do this and avoid the variance? Well, no, not directly, but indirectly, yes, we can. And we can significantly improve the performance and the other problems we saw earlier. So here's the redesigned system. So what are we looking at now, John?
So you'll notice the big change here is that now we're able to build an array that's made out of both of our types of consumer of our data. So the things updating the UI are built into the same array as the things writing data to disk. And we were able to do that through the use of an interface.
Now, you could have done this with just a parent class in the previous version of LabVIEW, right?
Yeah, I think that we could have, with some composition and some abstraction, accomplish the same goal, but it definitely would have been more classes and more code to write.
True. And as we'll see here in a little bit, you would have been tying two things together that really don't have any business being necessarily tied together for their state data, this file and this UI, and we'll have some other things we're going to plug in here eventually, right?
Mm-hmm. Yep.
Okay.
Exactly.
I'm stressing this for everybody who's listening, because sometimes you can look at this code and you're like, well, I'll just use a parent class. This interfaces isn't really showing me anything. One of the things we find is it's a little hard to demonstrate the value of interfaces in small bite-sized pieces of code, because the problems they solve are on very large pieces of code, and where you've got lots of independent things. So what we're going to hold this slide in your head, and we'll get there eventually. We're going to show you how we're going to plug some other things into this same hierarchy that definitely wouldn't want to come off the same parent. Now, I noticed that we made another change. Instead of passing data out of teardown, we're passing these things in to teardown.
Yep, that's right. So when we drill into teardown, you'll see that now we've completely changed the interface for how data gets consumed. Before, the test step's job was to send data out, and that was a cluster with a variance inside. So we were losing our typing information. But now that we're able to pass this interface down, we can actually maintain our typing with our data.
All right. So all of these things are going to turn into this data persistence interface. And teardown is going to have the ability to talk to data persistence. So let's take a look inside there. So we drill into teardown, and we skip a couple of levels of sub-VIs that we wanted to build out. And we get down eventually to this function. What are we seeing here, John?
So now we're actually inside of a test step, and this test step's job is to go and read a thermocouple. We're just kind of ignoring the fact that it has to talk to hardware. But what we've got is some data coming in, a type double, and we've created a method for our interface that deals with type double data to be persisted. What this means is that you end up with a method tied to each type of data you need to be able to consume, which is an interesting decision to make because at some point somebody has to know what the data types need to be. And we elected to put that knowledge at the interface level, where it should be more abstract.
There are, it should be noted, a number of different approaches to this particular problem that you have pros and cons and trade-offs, and it varies wildly depending on what application you're building. This was, we felt, the right solution for this particular application. It put the onus of knowledge at the place which was the most likely to have that knowledge. So we weren't spreading around. Who needs to know that this is actually a double? Well, it's the person who already is reading the data and is like, I'm reading a double. So it made sense for that thing to be the thing that strongly knows I need to call the double part of this interface. All right. So what do we have now?
Yep. So now the major changes here are we've ditched our variant and we've got the strongly typed data throughout the application. And ditching the variant, we also lose that performance hit that we were taking with the variant conversion. So now the type remains the type as it moves through the application.
Nice. There's also one more thing that we're going to be able to get. You see, this is a hardware test harness that we're building here. It's supposed to test that mirror and the reflectivity sensor and the communications between them. It's testing all the hardware. But that means that this is really a giant piece of software which also needs testing, because we want to know that this driver, essentially, that we're deploying onto all of that hardware actually does its job. So how do we do testing of this hardware test harness? Well, instead of the write to UI and write to file that we're passing through here, we can pass what's called a mock object. So we're going to create a new class that is going to have some values, and it's going to implement that data preservation interface. And we're going to pass it into our framework. And when we hit run on this model, well, it's going to go into that teardown and it's going to call that write double. But what this test function is going to do is, instead of actually persisting the data anywhere, it's going to check, does this match the expected value? I was expecting you to see a thermal limit of 60. Did it actually see a thermal limit of 60? I was expecting to get a temperature of 85. Did I actually get a temperature of 85? And it's going to set its own internal state, because remember, it's a real class, so it has an internal state, as pass or fail. And we're going to run through all the test steps. And then at the end, we can cast it back as a mock object and say, did this test pass? We didn't have to change anything about the logic of the test steps or the execution of the test steps or the way they interact with any of the data preservation model. And we can simply stick in a mock object to accurately do our testing. Mock objects are really powerful. So in this particular example, I've got these hard-coded numbers that I store inside, and I say, basically, you should expect to see these values. But I could do something more interesting. That mock object could actually be looking against a golden dot, so that when we test against the dot that we're currently building, it could look at runtime. It could constantly be looking back at the golden master and saying, well, what value is the golden one seeing at the same time that this test one, that the one under test is seeing? Compare those values. Are they within, exact? Are they within some epsilon? It can be a very sentient object, and it still passes through exactly the same code and allows us to exercise that code under real world conditions. So to the original two advantages of the new test harness, we can add easier to test. This is something that is really hard to do with another system, because your your test objects, your data objects, your UI objects may come from completely different inheritance hierarchies. Your UI object may have its own entire inheritance chain of UI pieces, and it can't afford to use up its one inherited parent to inherit from the abstract class of data preservation. It needs to coming off of an interface for data preservation allows it to use its state inheritance for something more important. So, John, you guys have already done some amount of prototyping on the new refactor and building it up. Is there anything else that you guys have learned or seen as you've been working on this?
Well, Paul, you've done most of the code. Do you have any thoughts?
I'm on the spot here. No, so when we first started talking about this, I was kind of wondering if this could be solved with composition. And I kind of spent a little time going down that path of looking at, could I create a separate abstraction without interfaces at all, and then use that abstraction to wrap up my two other classes, the UI, in this example, say the UI and the file writer. I found that I could do it, but in order to do that, you have to make a significant amount of more code, and it's basically all just boilerplate code wrapping up these objects. Whereas with interfaces, it's significantly cleaner, significantly less code.
That has been my observation with programs in other programming languages, and in the 6 months that we've professionally had them in LabVIEW, I've seen largely the same thing in G, which is what we expected to see based on the other experiences. So this ability to abstract away the details, and this ability coupled with the new ability to build mock objects and really test your harnesses is something that I believe will be quite powerful in LabVIEW. And when I first introduced the interfaces in the presentation back in April, a number of people immediately asked me for an example using mock objects. We're going to make this code available here so you guys can look through it. It is a very simplified model of real-world code. John and Paul can't actually make the actual code available. That's client code on their end. But we felt we could strip it down and get you this little model that at least gives you the idea so that you can use the same concept in your own code. It's a new powerful technique in your software testing toolbox that we really haven't had before in LabVIEW in any sort of clean form. So a little bit of review here. We have now got G interfaces. Essentially, they are classes without data. That's not what they are. That's not their identity, but it is their behavior and their state. And so you can think of them that way as a first step in getting them in the right place in your head. Interfaces enable a form of multiple inheritance. We're going to talk about parent classes. We're going to, a class has a single parent class, but a class may have multiple parent interfaces, and it will inherit methods down from them. The interfaces decouple modules and enable dependency inversion. That's the de-installer. And that's what we were showing you here today. We can package these things separately, and we can swap them out as we did. We got rid of the whole UI and file writing layer and put in a mock object so that we can maintain our invariance in our main code while making changes in the client. And in general, as was talked about with having to build wrappers and some of the container stuff, interfaces can make nicer code in a lot of places. So they're definitely worth your time to explore. And I hope that we see a lot more development in their richness over the next couple of years. So, Paul, do we see any questions out of the chat?
Yes, there are a couple questions on variant overhead. So not really related to interfaces, but just the use of variants and how much overhead there is to that compared to, I'm assuming, dynamic dispatch with classes.
A lot. So even take a single integer that you decide to package as an integer requires allocation on the heap of a data structure capable of holding on to this thing, and it has to copy over a bit of memory that is a pointer to the type so that it knows what type of data is in, and it has to copy that integer itself. As you get more complex data types, that copy becomes more and more expensive. So you have that overhead of creating them. So now it's a bloated object that's moving around on the wires instead of a much simpler object or more directly accessible object. And then when you get around to actually using it, you generally have some form of type testing that you have to do to figure out what can I do with it. So I have a variant. Well, if I'm going to actually write it to a file, I have to test, is it a double? Is it a double array? Is it a string? Is it whatever your set of types are? You start running down the list, and each one of those is it this tests is expensive. And it's basically a call to variant to G data over and over, and LabVIEW trying to do the type resolution, which we've honed and tried to make as fast as possible. But it's just not a fast operation in any language, that kind of data type reflection at runtime. It's fast enough for a lot of applications, don't get me wrong. We've written a lot of successful applications using variants, but we can blow the socks off it if we can stay in direct data flow. We're talking multiple orders of magnitude here. So wherever you can avoid variance in favor of data flow already today is definitely preferable if you have performance requirements, which in some of these hard real-time systems often is. And hard real-time, the memory allocation of variants often makes them a non-starter in the first place. They can't really be pre-allocated the way we can do a fixed size array or anything, because by their very nature, they're flexible for whatever you want to shove in them.
Even another question that just came up, which I think would be a good thing to discuss. What are some of the abuses or wrong ways we can use these? So these interfaces I think are probably new to most of us. What are some things that we should look out for and things not to do as we use them?
Well, so the one that I had to correct Paul on when he first was writing the prototypes is don't put the stupid capital I at the front of the interface class names. A lot of other programming languages will name their interfaces I, some noun, and their classes are just some noun. Well, it turns out in a graphical programming language, you don't have to put the I, because we can tell it's an interface by looking at the icon. And any place where you need to know it, you look at the local FP terminal or the block diagram constant or the icon in the project tree or the context help failing any of that. And you can see this is an interface, not a class. But there's plenty of places in G where we don't want to see the difference, where I may have a developer on my team who understands classes and is happy to use them, uses them all the time, and he or she is not trained up to use interfaces. It doesn't know what they are. If they start seeing these magic eyes around the place, they're like, "Whoa, what is this?" And we saw that effect during some of the beta tests. But if you just name it as a class, they use it as a class. And what does it look like to them? Well, it looks like a class with a bunch of methods. They couldn't see the private data in the first place, and they don't expect to. So it works as a class for them. Not putting the I on means we can localize into foreign languages. Not a major concern for a lot of you, but those of you who write libraries, it starts becoming a concern. And then the last one is, without that I, we can do much cleaner refactoring, because all I can do, if I can simply replace the file on disk that used to be a class with an interface, and then go create a new child class that inherits that interface that is the specific code, I don't have to change any of my original application. And that saves a major refactor that constantly bites us in some of the other programming languages that have that I as a requirement. So that would be one thing to stay away from. And I've had to stress that a few times, because a lot of books out there from these other languages, you should name them with an I. But if we interview actual developers in those other languages, which I took the time to do, they're all like, yeah, it's just a convention that we've always had. And it would be weird to try and change it now, because even the system level interfaces all have that I. So we have to go with it, but it really doesn't save us anything. So I'm trying to make sure LabVIEW starts off on the right foot. John, is there anything else that you've discovered that they should stay away from? Because, I'm a developer, I'm a little bit biased.
Well, to be honest, we're still learning ourselves. So this project as it stands right now is still in 2019. We're bringing it into 2020, probably in January, at which point I expect to learn a lot of lessons.
Okay. So yeah, I think that's kind of the state of the art where we are 6 months out. At the moment, I'm not advising anybody to stay away from any known potholes. I'm sure they're there, but at the moment, we seem to be clean. What you
So
got? Anything else, Paul?
Chris Stryker just asked an interesting question. Is inheriting from too many interfaces a code smell? Like, how deeply should you nest these things?
I have seen that question asked in other languages, and I've never seen a satisfactory answer. I can clearly point at classes that are just flat doing too much and that they're just wrong. And I can point at classes that have the same number of interfaces, and you're like, no, that's absolutely the right assignment of functionality. It seems to come down to how closely related are those interfaces to the identity of the class. Can you say what this class is supposed to do? What is its role in the system? And it should have interfaces related to its role in the system. And if you start putting on things that are not its role in the system, you sort of have to start asking yourself, have you violated single responsibility principle? What am I piling on here? And have I just made this a dumping ground for code? Because I happen to have a hammer in my hand, so I might as well attach a backhoe to the back end of it because, hey, it works as a backhoe if you use the other interface. But there are other interfaces that are very tightly bound together. The hammer with the claw that we saw in the original thing. It's one tool, and it makes sense to put those together. I don't know that we can conclusively answer that, and it's one of those things that goes in the heading of, you're an architect, you will develop a gut instinct for this over time, and your gut instinct will start guiding the developers on your team. And maybe one of us that's particularly brilliant will come up with a way to say, and here's how I can codify it as a rule. Sometimes we get those every once in a while.
Yeah, I mean, to what Paul mentioned earlier, I think the biggest thing that I've seen is the ability to make the code cleaner, easier to understand, which is important. You end up with fewer classes layered on top of each other if you use interfaces correctly.
Steven, another question I saw, do you see any issues using interfaces with DVRs? Is there anything to be mindful of there?
No, they should work. It should, and tested, to the best of my ability, work is the same as the classes do. They have the same rules about, the automatic downcasting has to be preserved from terminal to terminal. You can use them as their interface type. You'll have to use the preserve runtime class node to cast back to the original if you go through some sort of global storage. But as long as the preserve runtime type can be preserved through all your sub-DI calls and LabVIEW can track that through the compile, you should be good on the diagrams just the same way you are with classes. The DVRs do allow the same casting as a DVR that DVRs of classes allow. Interfaces themselves do lock in the options for locking the hierarchy. That you can't lock the whole hierarchy underneath an interface. So that those settings in the class properties dialog are grayed out in the interface properties dialog. But overall usability of them is identical. Try not to use them. I know I don't know if Mikhail and some of the other fans of references are in the chat, but my usual admonition: use references when you need them. Don't use them just because they happen to be there. Let's see. Does a single broken interface break the whole inheritance hierarchy within an application like it does for the classes? Well, it depends on the break. If the interface has a broken method, no, just like on classes. If the interface itself is broken, yes. And so an interface being broken itself will be like if the interface is missing a VI, a member VI, or if it's missing one of its own interface parents. Then you will get a break propagating through the whole thing. But if it's just a broken member, it does not break the whole hierarchy. It only breaks users of that particular method. Do you think it is a good idea and possible to use the factory pattern with interfaces? Yes. 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 I expect them to be fairly heavily used in that area, actually. Hey, if somebody in the community wants to build me something, there's this thing in C# called MEF, the something framework. I don't even remember what MEF stands for. Everyone just refers to it as MEF. And I would really like one of those in G. It is essentially a factory pattern dynamic class loader that automatically plugs classes in as they load into a calling framework so that the callers can simply discover their parts are already available. It is a wonderful thing. It is now standard practice in C# to just use MEF for plugging things in. There, Daniel Job has provided a link. Somebody wants to build that, then we will have a framework in G, and then we can go talk to Jeff K about building it into the language. And it does a lot of work for dependency injection and stuff. So I would love to see us build that up. I just haven't had time to look in that direction. I'm busy with these rocket things now. So. Do we have anything else? I don't know. Let's see. We still have plenty of time.
Question from Jeff Siegel. Interfaces allow multiple inheritance where only one parent can be a class. Should that one parent really be an interface as well? Or put another way, should in principle all classes inherit from an interface?
Right. That's where I was talking about dependency injection being a principle, not a rule. There are plenty of times when inheritance is the right choice. In fact, one of my favorites is serialization should always be a class and not an interface, because serialization is something that doesn't make sense to inject at a lower level. If your parent can't serialize its private data, you can't add that capability at a lower level because you don't have enough to recompute or reconstitute your entire state. It's an easy one for me to point to. I've presented on it a couple times over the years. There are other cases out there, similarly, where you really are wanting to inherit truly the state of the object and use it directly, and you're going to have methods. You have to use your judgment as an architect to decide where the right place to cut is. There was a push a few years back, maybe 5-6 years ago, in some of the other languages to say everything should be an interface. And some architects went down that road, and it works, but it resulted in the same sort of unnecessary code bloat as not using interfaces. So they are to be used more heavily than they are currently. So frankly, I'm going to tell you right now, err on the side of using interfaces, because most of us are going to use them too rarely. I've had them for a long time in some of the other languages I use, and I still don't instinctively reach for them often enough. And I find myself wishing I'd done it, 6 months later and having to refactor. But don't use them ubiquitously. You will find yourself running into problems on the other side. It's one of those things we're just going to all train ourselves to get that rhythm and feel for. But right at the moment, if you wanted to take that position, I think you would find your code better off than if you try to swing to the side of, well, I'm just not going to use interfaces. So between those two extremes, I think the balance is closer to lots of interfaces and not so few interfaces. That's what I'm trying to say. Did that make sense, John?
Yeah, I know what you're saying.
Okay.
Again, I need hands-on time.
Right. I don't have customer faces right now to give me visual feedback, so I'm just going to stare at John. And does he look confused?
And I think that might be kind of the crux of the problem here. I'm curious how many people here are actually using interfaces today in LabVIEW 2020. My guess is the majority of people aren't, and so we kind of lack that context for trying to apply it to a problem. I know that's how I learn the new ideas best.
Yeah, I expect the uptake for interfaces to be faster than some of the other paradigm switches. Just the learning curve is much smaller. But getting people to adjust over to using classes took about 10 years, and then there's this huge uptick in usability, or in not usability, in use. It suddenly jumps significantly as we pass a threshold of confidence and just libraries that use them, et cetera, et cetera. And I expect that same sort of thing. We see it with every new paradigm shifting feature that we've introduced. Event structure, VIMs, we're still seeing it with channel wires. There's usually a long head on trying to do things differently. And then there will be one magic library that lots of people are looking at that goes, huh, they used interfaces. I think I'll use interfaces. And then we're off to the races.
Yeah, we got a slew of responses. It looks like a lot of people are on the cusp of using interfaces.
Philip Lundeen asked an interesting question here. I just noticed. Would interfaces be a good way to maintain backward compatibility when messaging, i.e. provide an interface for handling a message and have multiple different classes representing schema versions? No. So the problem, the classic problem, or at least if I assume you're asking about this, is in a DQMH or any queued message handler or actor framework, you have an object, a message, and you want to send it to a receiver, and you would like a compile time check to know that this message can go to this receiver. And you're like, I want to put an interface on this that says I only accept messages of a particular type. Well, it turns out that if you start looking at the type calculus, which is a thing, there's a whole mathematical branch of type analysis and compiler theory, it's almost like stepping to a different order of infinity, like going from the counting numbers to the real numbers. The types needed for send are not the types representable by an inheritance hierarchy of interfaces. And you need a different thing entirely to represent what can go in this type at compile time. And it's not even well defined. I've never found a language that really can well define it. That's an actual working model. It'd be an interesting area if people have research papers on that I could look at. I delved into it just a bit over the past couple of years as I was working on classes and interfaces. It's a fascinating area of research, well, if you're someone like me. But no, it turns out that they are actually a higher order typing problem that, so unfortunately we don't get a silver bullet to that problem. So we're still gonna have the runtime type checking in Actor Framework and similar implementations. If we could ever solve that problem, it would probably be the kind of bullet that would move people away from the enum and value or string and message paradigms, because they actually have the same overhead that we have with the type checking, and they have some other advantages, which is why a lot of people prefer that style of messaging. JD Powell is in the chat here. It's a good system and has some really nice effects. But if we ever were able to buy that true compile time type checking, that would be a pretty heavy hammer to wield. And I'd love to see it happen, but I don't know a solution there at this time. I haven't been following the chat. Is there a next question in here?
It looks like both Quentin and Alan Smith have on-topic presentations coming up.
Okay. So yeah, if you're interested in this, hearing more, you should go through that. I'm scrolling backwards looking for extra questions in here. I may have missed something. If I did, repost it down there. So Paul and John, you guys are moving forward on this project. If we, get around to having an NI week, whether virtual or in person, do you think you guys will have more information about this about that time?
Yep. Yeah, that looks like the time frame. We're actually going to start work back up in a few weeks here. So by NI week of 2021, hopefully we have it. We should have some interesting content.
Good. Yeah, I had a list in my first presentation of seven major areas that interfaces just completely change your designs. We've been exploring testing today, mals and mals, your UI abstraction layers. There's a lot of things out there that we can do that are really fascinating, and we know this from other programming languages, but with G, there's some nice data flow advantages to these interfaces that I've already been able to see in some of my own code that I hope the rest of you are, get to experience soon as your business logic allows you to upgrade to 2020.
Mm-hmm.
Well, we got about 5 minutes left. That's enough time to take a bit of a break here. There's the breakout session. I'm going to be popping back and forth. And I may check if you've got any further questions, post them over there. John and I, Paul may answer them at some point a little bit later. But as for now, take a 5-minute break and get ready for the next session. Paul, John, thank you for coming.
Thank you, Steven.
Thanks, everybody.
Yep, thanks.
Take care, all.